You ever stop and think about that invisible force that's powering literally everything around us? Our phones, our homes, the whole shebang. Well, it turns out it's not magic. It all follows a few simple, fundamental rules. And today, we're going to crack the code on the big one, Ohm's Law.
It all starts with a really simple question. You look at a light bulb like this, and you wonder, what actually makes it glow brighter? Sure, you could say it needs more juice, but what is really going on inside that circuit? Turns out there are three key players in this story, three forces controlling everything. So, let's meet them. Okay, first up, we have voltage. The easiest way to think about voltage is as the electrical push. It's the pressure that gets the whole process started. Imagine water in a hose. Voltage is the pressure from the spigot. The more you crank it open, the more potential force you have. And we measure this push in volts.
Next, meet current. Now, if voltage is the push, current is the actual flow. Sticking with our hose analogy, this is the amount of water that's actually moving through the hose. It's the stream of electrons getting the job done, and we measure this flow in amperes, or as you probably know them, amps.
And our third and final character is resistance. This is the squeeze. It's the opposition, the thing that pushes back against the flow. In that water hose, this would be like putting your thumb over the end. You're making it harder for the water to get out. Everything, and I mean everything, has some resistance. We measure it in ohms. So we have our team, the push, the flow, and the squeeze. So how do they all play together?
Well, way back in 1826, a physicist named George Simon Ohm figured it all out. He found this incredibly simple relationship between our three characters. He realized that the current is directly proportional to the voltage, which makes total sense, right? More drive gets you more flow. But he also found that the current is inversely proportional to resistance. The more you squeeze, the less flow you get.
And that brilliant discovery boils down to this one single elegant formula. Current equals voltage divided by resistance. That's it. You can think of it like a constant tug of war. Voltage is always trying to crank the flow up, while resistance is always trying to choke it back down. And this perfect little balancing act is the foundation for, well, pretty much all of electronics.
And hey, here's a super handy little trick to remember it, the Ohm's Law circle. It's a fantastic visual that helps you find any of the three versions of the formula. All you do is cover up the thing you're looking for. Need to find current, or I? Cover it up, and you're left with V over R. Want to find voltage? Cover the V, and you see I right next to R, which means I times R. It's a great little cheat sheet.
All right, so that's the theory. But theory can be a little dry. Let's make this real. Let's put this law into action with something you've definitely got in your house. We're going to start with a standard wall outlet. In the US, that's giving you a consistent electrical push of 120 volts.
Okay, now let's plug something in. We need something with a lot of squeeze, a lot of resistance. A little electric space heater is the perfect example. Let's just say this one has a resistance of 8 ohms.
So we have our push, the voltage, and we have our squeeze, the resistance. The big question is, can we use Ohm's law to figure out the flow? How much current is actually rushing through that heater to create all that warmth?
Oh, you bet we can. We just use the law. Current equals voltage divided by resistance. So we take 120 volts, we divide it by 8 ohms, and we get 15 amps. And that, my friends, is a ton of current, which is exactly why a little space heater can blast out so much heat.
And remember, this is not a one-way street. The law is incredibly flexible. If you know the current and the resistance, you can figure out the voltage. Know the voltage and current? You can calculate the resistance. It's like the Swiss Army knife of basic electronics.
Okay, so now we get the relationship between the push, the flow, and the squeeze. But so what? What's the actual result of all this? What does all this electricity in motion actually accomplish? Well, it creates what we call electric power. Power is really just how fast energy is being used. It's the amount of work the electricity is doing every single second. And we measure it in watts. Yep, the same watts you see printed on your light bulbs in your microwave. A 60-watt bulb is just sipping energy compared to a 1500-watt microwave, which is absolutely gulping it down.
And guess what? The basic formula for power is just as simple and clean as Ohm's law. Power equals voltage times current. That's it. The push multiplied by the flow tells you exactly how much work is getting done.
Now this is where it gets really cool. We can actually combine the power formula with Ohm's law. So we start with power equals voltage times current. But wait, We know from Ohm's law that V is the same thing as I times R, right? So let's just swap that in. What we get is a new equation. Power equals current squared times resistance. And this one is crucial, especially for engineers, because it directly connects how much current you have to how much heat you're going to generate. And you can do a similar trick to get a third version too.
So what does that mean in the real world? Let's go back to light bulbs. A standard 60-watt bulb only draws about half an amp of current. But a big, super bright 300-watt bulb, that thing needs 5 times as much current, a full 2.5 amps, to create all that extra light. So the bottom line is simple. More watts means a bigger current draw.
All of this talk about watts and amps and power brings us to the one place where this stuff really hits home for all of us, the electricity bill. So let's connect these numbers directly to your wallet.
Here's something you gotta know. Your electric company doesn't actually charge you for power. They charge you for energy, which is really just power used over time. The unit they use is the kilowatt hour. So let's take a 100-watt bulb. If you left that thing on 24/7 for a whole month, that's 720 hours, you'd use 72 kilowatt hours of energy. And even at a pretty cheap rate, like 6 cents per kilowatt hour, that one little bulb just added over $4 to your bill.
So where does that energy actually go? Well, as the quote says, it gets dissipated. And that's usually just a fancy word for turned into heat. Our space heater from before? It's basically a giant resistor that's designed to do nothing but get hot. Your toaster, your hairdryer, same deal. They're just using resistance to make heat on purpose. You know, even an old incandescent light bulb is really just a tiny, very inefficient heater that just so happens to glow as a side effect.
So you see, Ohm's law and the power equations give us this beautiful, predictable blueprint for how electricity works when everything is going right. It's the rulebook. But that brings us to one last, very important question. If this is how circuits are supposed to work, what happens when the rules get broken? What happens when it all goes wrong?